Okay, welcome back to part two of forces, where today we're going to be talking about a few extra forces that you'll see within Physics 1. So the first one that you'll see is the force of friction. And if you ask yourself, what is friction, you'll likely think it's some kind of opposing resisting force as an object slides across something, which is very much true. But there's also friction when an object is being held in place on, for say, a ramp. And there's also friction pretty much in everyday life. When you're walking, all those sorts of things are all done by friction. When a tire is spinning, the actual thing that is accelerating the tire and is actually causing the car to move forward is in fact the third law, force of friction. So friction is a very important force within physics, and essentially it's just a resistance to motion by some surface. And if you do a thought experiment or some kind of actual physical experiment, if you were to put your finger, that's a very bad finger, but if you were to put your finger along a table, a surface like this, and you were to press down, the harder you press down on this table, the harder it will be for you to slide it across, the greater the force of friction. So what you can probably derive from that is that if you're pushing down, the surface is pushing back with some kind of normal force, right? As you push down on that surface. And if you're pushing down harder, that normal force is going to be getting bigger. And what I'm getting at with this is essentially the force of friction is entirely dependent on how strong the normal force is, or how strong the applied load downwards is. So the force of friction can actually be written as mu, which is some kind of coefficient of static or kinetic friction times your normal force. Now, the coefficient of static friction or kinetic friction are two different coefficients. For static friction, if an object is sitting on something, that is a coefficient of static friction. It is not moving. It is, in fact, being held into place by some kind of static friction coefficient. If the object is now, for instance, sliding down something, there's now a kinetic friction. There's something that is actively opposing the motion of that box or that object sliding down. Now, if you were to think of a tire as it's rolling, like we said in the previous example, this is a lot of people make this mistake. It is not, in fact, a static friction. It is not, in fact, a kinetic friction that's actually holding the tire, that's causing that movement forward. It is actually a static friction. It is holding that tire in place, which is what's causing the motion of the car to be accelerated, to be pushed forwards. So let's look at some, for instance, examples of a box sitting here on some ramp, some incline. You have some angle theta. You're given some coefficient of static friction, mu(s), and it wants to see what is the force of friction. Well, the force of friction, let's do our steps first. So, first thing we're going to do is isolate this box. We have the free body diagram, or we have the axis already set up there, so we'll draw a free body diagram. So we have our point. Gravity goes always down the page. Normal force goes normal to the surface. We have some angle theta here, and we're going to do a trick to figure out where that angle will lie again. So this is, if you divide this up into eighths, you can essentially determine where this same angle will be by putting, so based off of parallel lines, you know, this angle will be theta here, this won't be, this will be, this won't be, this will be, this won't be, this will be. So it's called a pizza pie trick, where you can just basically, from the first part of parallel lines, figure out where that first theta is, divide it up into eighths, and then go every other slice to find out where your angle will lie, and it'll lie right here. So let me draw this a little bit cleaner now so you can see it. So we have our normal force going like this, we have our gravity force going like this, and we have some force of friction holding this box up. So we're going to have mu times n going that way. That's up the hill. And we said that this is where that angle theta lies. And we know that this is going to be the component in the x, and this will be the y. So with this angle theta, this m(g) vector is no longer lying solely within the x or the y plane. So we have to break this up into a vector that goes down in the y and across in the x. So it is a negative x component vector and a negative y component vector, which makes sense because it will be sliding in the negative x and y direction. So We now have our free body diagram. Let's write our sums of forces equation. So sums of forces in the x, the only thing going in the positive x direction here is mu s times n, which is our friction force. Or, if you want to, so this question here is actually asking for two different ways, which is mu s times n, but for now we'll write it as force of friction. And minus, right, because this portion of mg is going backwards, and that's mg sine theta, right, because it's the opposite. Now, this is being held in place. This is static, so this will be equal to 0. And we can write our sums of forces in the y direction. We have n minus mg cosine theta. That's also equal to 0. So, the force of friction can either be mg sine theta, or the force of friction can also be mu times mg cosine theta, right? Because n equals mg cosine theta, and we know that mu s times mg cosine theta is equal to the force of friction. So these are essentially equal to each other. They will be equal to each other. There you go. That's how you solve for force of frictions. So let's move on to another type of force called the spring force. So the spring force is essentially if you compress a spring against, or if you compress a spring, that spring will retaliate and it will throw whatever you're compressing it with back at you. And this is through some law called Hooke's law, which essentially says that the force of the spring is equal to this spring constant times the displacement of the string. So, for instance, if this is our spring here, and I displaced it some distance x, as in I pushed into the spring so that the box is now here, the force will be directly proportional to how far in we pushed it. So let's look at this spring here sitting, this box sitting on a spring here. We're given our k, we're given the mass, so we're also given this angle theta. So what we want to look for is, let's see the sums of forces in the x direction, just based off of this information that we have here. So we'll isolate our object, and we'll draw a free body diagram. So we have mg going straight down. We have the normal force going up. We have the spring force pushing against it, kx, right? And we'll draw an axis. I like to draw a axis that is, whenever you're in a plane, it is typically 100% times always better to draw your axis tilted with the plane. So I always recommend to draw the axis tilted with the plane. So let's write our sums of forces equation now. So sums of forces in the x, we can also actually add in those angles. So we said this is the angle, which means that based off that line trick that we did earlier, this will be the angle as well. So we have the sums of forces in the x, we have kx going positive, right? We have, same thing as before, minus mg sine theta. And I just want to make sure I didn't mess that up. Nope, I didn't. Yep. So minus mg sine theta, this is equal to, we'll say this isn't moving, so this is equal to 0. And sums of forces in the y, we have n minus mg cosine theta, and this is also equal to 0. So the sums of forces in the x direction would be just this portion, which is kx minus mg sine theta. So last thing, normal forces, which we talked about a little bit in the last video, but I want to get a little more into depth with it, essentially how you interact with the normal force in your environment. So let's say you're in an elevator and you're accelerating upwards. You feel some kind of compression on you. And essentially what you're doing is you're exerting a greater normal force as you're having a greater normal force exerted on you as your elevator is accelerating upwards. Once it reaches constant velocity, you stop feeling that. So let's say we just had some guy in here with some mass m, and he's accelerating in this elevator at some a. I want to know what exactly is the normal force on him. So how can we do that? We can isolate him like that. Draw a free body diagram. So we'll have his weight going down and just the normal force going up. And I'll draw my axis as y and x. And I'll write my sums of forces equation. So sums of forces in the x is 0. There's nothing there. Sums of forces in the y. I have n minus mg. And this, if he is accelerating upwards, right, will just be equal to m times a. Now, so that means that the normal force exerted on him will be N is equal to ma plus mg. So he has a greater normal force, right? Now let's say he's going at constant velocity. What happens? We have N minus mg is equal to 0. So therefore, if he's going at constant velocity, he doesn't feel anything. He just feels his own mass, right? Let's say he's decelerating. What happens? The only thing that changes is that now we're going downwards. Or, sorry, let's say he's descending. He's accelerating downwards, not decelerating. Then what happens? Well, we have N is now, we'll flip the axis. So we'll do the axis like this, y and x. And we'll say he has mg going down minus n, right? Because now mg is going the positive direction, n is going the opposite direction, is equal to ma. So now n is equal to mg minus ma. So now he feels lighter. So these are the three cases that you can get from normal forces and why you feel lighter, heavier, or the exact same depending on how your object is accelerating. And that'll be it for this second round of forces. In the next video, we'll be talking about centripetal acceleration and centripetal forces that occur in objects. So thank you.